Now we are hearing for the talk of Dmitry Ryabogin with the following theme on floating bodies and related topics. Please, Dmitry.
Okay, thank you very much. Yes, thank you very much for the invitation and for everything. And my special thanks are to Alexander Stokolas for bringing me into this. So I'm going to speak about homosity conjecture and about questions related to floating bodies. So let me write on the homosity conjecture. A counterexample. And this is what we're going to be about during this half an hour. Yes, do you hear me? Do you see what I wrote? Everything is fine. Okay,
Yes.
so this is going to be a joint work with Maria Alfonseca, Fyodor Nazarov, Alina Stanku, and Vlad Yaskin. Okay. So let's start. Let me formulate the conjecture. And the conjecture belongs to Karsten Schutt. Just a second. Karsten Schutt and Elizabeth Werner. This is about 1990, something like this. So let me formulate it. We are going to speak about convex bodies. So K is going to be a convex body. Today on the plane in Rn, yes, n greater or equal than 2, but please think today about n is equal to 2. The high dimensional case will be similar, and the convex bodies, this is, I will recall, just this is a closed bounded convex set with a non-empty interior. Okay, so let me draw it, something like this. Okay. And what we are going to do, we are going to fix, I'm going to write S1. This is going to be just a unit circle on the plane, yes. So this is S1 is the set of all x on the plane such that the Euclidean norm is 1. Here, when I put Euclidean norm, I mean x1 squared plus x2 squared by the Pythagorean theorem. And I'm going to write theta belongs to S1. I mean by this, I will mean that this is a unit vector. Okay, on the plane. So, for example, something like this. This is theta. Okay, let's assume that for simplicity that 0 belongs to the interior of K. Very good. So what we are going to do, we are going to fix delta, our favorite delta between 0 and the area of K over 2. And what we are going to do, we are going to conclude that for any theta unit vector, there's going to be a distance, t depending on theta, this is a real number, such that the area of K intersection W plus T theta is delta. So in a moment, I'm going to introduce this guy. So this is just a kind of a wet part, if you submerge the body into the water. So let me introduce this W. This is my water T theta. And of course, I can move this water anytime I want. It depends on the density of my body. But for example, think like in the picture, this is my water. And all the thing that stays above the water here, this I call this W plus. So this is W plus E theta. In a moment, I'm going to introduce it accurately. And the WT theta, this is this water surface, the line. So let me, maybe I'm out of space, let me write it here. So W plus T theta, this is going to be the set of all x on the plane such that the scalar product of x with theta is greater or equal than t. Okay, so by the intermediate value theorem, you can move the water surface up and down so that the corresponding, for example, if you are here, your piece is almost half of the area. If you are here, the water, then the piece has a small area. But I mean, you fixed your delta first, and then you chop off the piece of the body having this area, depending on the direction theta. So you should do it in all directions. You fix, and this is theta. Your delta is independent of the direction, okay? In every direction, you fix this, and you chop off the delta. Okay, so I should also say, of course, that what is x dot theta? This is a usual scalar product, x1 theta 1 plus x2 theta 2. Okay, very good. So now we're almost ready to formulate the conjecture. So we are going to define now the so-called the body of flotation. This is the following. So we are going to take, I'm going to write this K delta, okay? So K delta, this is going to be the intersection of all parts that remain dry, okay? K theta, theta from S1. So let me draw the picture again. This is my body K, this is my origin theta. I'm going to be here, so I chopped off this piece. This is my delta. Then I took the different theta and I chopped off a different piece. And then let me make it red, let's say here, theta, and I chopped a different piece. And so I chopped off all of these pieces, and W minus of T theta, this is the set of all x in R2, such that x dot theta less or equal than T. So the part that is not wet. And then what you're going to do, you're going to take the intersection of all of these half spaces, something like this. And this is K delta. So the part of the body that is always dry, if you submerge the body into the water, and the body is of constant density, of course. Okay, so this is our K delta. I hope that the definition is clear. Well, it's a little bit, maybe it looks artificial, but this is a natural thing in classical mechanics. And it plays some auxiliary role in shipbuilding and other things. So I don't want, unfortunately, we don't have time to speak about the history. So this is my body of flotation, and by definition, observe that this is a convex thing. I mean, you can define this in all dimensions. This is a convex body because this is the intersection. This is the intersection of half spaces, and this is the intersection of convex sets. So this is a convex set. Okay, very good. Even, let me tell you, even if you took the star-shaped set, something like this, yes, this is your origin, you could still define the same thing. You chop off the area of a fixed, yes, value, yes, and you could still define the same notion, K delta, but, and it's going to be, of course, it's better if delta is between 0 and the area. Otherwise, it will become empty, but I mean, we assume that. So K delta is going to be, again, the intersection of the half spaces. And even the set is star-shaped. But star-shaped, I mean that I have a point, and from this point, I see every point on the boundary. Okay? In fact, in my picture here, it is not star-shaped because this point I don't see, yes? But heuristically, it is clear. So even for the star-shaped body, the body of flotation is convex. So let me write it down. Even for a star-shaped body, star-shaped with respect to the origin, yes, body, the K delta is convex. Okay, very good, very good. So now the question, now the conjecture. So we are ready to formulate it. So fix delta, yes, as we agreed, and assume that your body K you submerge into the water is homothetic, proportional, better to say, to K delta, meaning that there exists a constant lambda positive such that lambda K is equal to K delta. This is the condition. The question is, does it follow that K is an ellipsoid, K is an ellipse? By ellipse, I've used the language. I mean that the ellipse is the body and the boundary, the same thing. For me, this is the ellipse, yes, and this is the ellipse. Okay. So this is the question. And in general, in this formulation, because I didn't have any conditions on delta, in this formulation, this thing is open. But what we are going to talk about, we are going to talk about the case where delta is close to half. If you assume for simplicity, I write always the area, but assume for simplicity that the area of K is 1. And then I will say delta is close to 1/2, meaning that the delta is close to the area of K over 2. Yes, so what I'm trying to say is that we will show that if delta is close to half, then the answer is negative. No, this is not true that the ellipse is the only convex body that satisfies this condition. Again, unfortunately, I don't have time to enter into the history of this. This is related for if you are interested in this, this is related to Boseman-Petit problems and Petit problems and other things, but I just mentioned this briefly. Okay, so this is the question. Again, let me recall it again. So I have my body. Okay, I chop off piece of a fixed area in all directions. Then I take the envelope of all of these water surfaces. Even better to say the intersection of the half spaces. Yes, for example, if I have this water surface, then I will take this half space. And if I take, again, if I take this water surface, then I will have the intersection of this. This is my half space. I have this K delta. I have my K. And I want my K to be proportional to K delta. Yes, and the question is if K is an ellipse, ellipsoid in general. Yes. Okay, so again, I have to repeat that if delta is not close to half, then this is open. Okay. We are going to construct a counterexample. At least I am going to outline the construction of this counterexample. So let me briefly tell you the plan of the thing, how we are going to talk about it, so it becomes easier, and then we will stick to this plan. So at first, we'll write out, so it will consist of 4 parts. We'll see how much time I have. So at first, we'll write our condition, yes, our condition. This condition, as I mentioned, as a functional equation, Just a second, I'm sorry. As a functional equation in terms of the radial function of K. In a moment, I'm going to introduce the radial function and everything. So this is the first step. And the second step, we're going to linearize it. So sort of differentiate it. Then we will look this linearized equation, and we will show that the linearized equation has a non-trivial solution. So ellipses are not the only bodies that satisfy this linearized equation. The linearized equation has a non-trivial solution. Let me put it this way. And finally, using the implicit function theorem, we are going to show that the original equation has a non-trivial solution. Again, when I say trivial, let's discuss this. Trivial, for me, this is an ellipse. Why this is trivial? Again, this is trivial, not trivial. Nothing is trivial here. Yes, so what I mean is that if you have a disk, let's consider a case of the disk. Disk is, I will call this B. So if you have a disk, how to draw disks? Something like this. Oop. Maybe like this. And no, this is still not a disk. Oh, here's a disk. If we have a disk, and obviously, if we have the fixed area that we chop off here, and then if you take the floating body of yours, it's going to be again a disk. Please pardon my drawing. Yes, so this is again a disk, and so maybe let me draw it like this. Let me put here B. Let me put here B delta. Okay, this is again a disk. So obviously the conjecture is satisfied by, I mean, not the conjecture, the condition is satisfied by the disk. Because if you chop off the fixed area from all directions, yes, then of course the envelope will be this. The intersection of these half spaces will be the disk again. Yes, so obviously one can compute even this lambda, one can compute. If you fix the delta is this area. You fix delta is fixed, yes, any delta. Yes, any. Yes, then of course you can just suppress the body you submerge and you get the disk again. And then one can play. I don't want to enter into this. I will briefly touch it in the future. What is very interesting here is that, of course, the ellipse is also going to be the solution because this behaves well. This condition I don't want to enter behaves well under the linear transformations. So the ellipses are going to enter into the game because the disks are going to enter into the game, and that was the original theme. Somehow, this is the original motivation for the conjecture that people thought that these are the only solutions. But we are going to show that this is not the case. Okay, but for small delta, again, I emphasize, I mean, for delta very close to 1/2. Our floating body, our body of flotation, let me put it, it's going to be very, very tiny. It's going to be like this. For other delta is open. Okay, very good. So let me make one more remark, how we are going to identify our body. So maybe a remark. Okay, the remark tells you that K is going to have some extra symmetries. So K will have some extra symmetry of a pentagon. Okay, not necessarily pentagon, one can do others, but pentagon is especially simple. So I'm going to write phi 2 pi over phi. I'm going to write this is a rotation. This is a special orthogonal group, so this is a rotation by the angle, by angle 2 pi over phi. And so our solution of our equation, of this equation, lambda k is equal to k delta, lambda could be computed and delta could be computed. Yes, our solution will satisfy phi 2 pi over 5 of k is k. So by this, we'll know from the beginning that these are not ellipses, because an ellipse doesn't have the symmetries. Okay, if an ellipse has the symmetry, it becomes a disk, but our solution will not be trivial, will not be a disk. Okay, very good. So no, let's stick to the plan. So now back to the plan. Okay, I want to introduce, let's write down our condition. So we write down our condition in terms of the radial function. Let me introduce the radial function. Okay, I will write rho k. Okay, so let me draw the picture, something like this. Necessarily for the convex body for star shape. Let me draw the star shape, something like this. Yes, this is my star shape body. Okay, this is my origin here, and I have this direction theta. And the radial function shows me how far I walk till the boundary. Okay, so for example, if I walk here theta, then this distance is going to be the radial function, rho k of theta. Okay, so let me define this precisely. Rho k of theta. This is the maximum of lambda positive such that lambda theta belongs to k. So meaning that again, I will repeat. So you have this direction theta, and you walk till the boundary along the ray emanating from the origin parallel to the direction you fixed. And this gives you the radial function. Okay, so let's write down our condition. So our condition is going to be written like this: lambda rho k is rho k delta. This is our condition. Before we wrote it like this, but this is equivalent. I'm going to omit k. I'm going to write usually, I will write it like this: lambda rho is rho delta for simplicity. I will omit k again, just to make the formulas not that complicated. And how we should think about our condition again. This is the condition. So we will think about it like this. So k, we more or less understand what it is, even if this is a star-shaped thing. And then here, the right-hand side is this floating body that is not clear what it is, some kind of complicated operation that is done with k. So this is how we are going to think about it. And now what we are going to do, we are going to linearize it. So we are going, instead of something like this, we are going to write something lambda k is this. Yes, with viscous, yes, which is, and this guy is going to be linear and very, very nice, and we'll understand how this equation behaves. Yes, so this is the linear version. Okay, that is going to be much nicer. Let me elaborate a little bit on analysis here. We are now departing from geometry and classical mechanics, and we'll go to analysis. So again, if you have a disk, then I will prefer to write lambda in terms of the angle. Everything is in the middle school, yes. So what do I mean? I mean that this is the angle I'm going to use alpha, okay? So this is my origin, this is my disk. And so what I'm going to do, this is my delta, is going to be the area of this, whatever, segment, whatever it's called. Yes, and I'm going to use lambda. What is lambda? Lambda is going to be this. Yes, the floating disk is here. This is B delta. Delta is this area here. Oop, I erased it, unfortunately. I'm sorry. Let me try again. Something like this. Yes, so this is B delta. And who is going to be this, this lambda? Here, this is a lambda. This is the coefficient. I mean, this is 1. Yes. So this is my lambda, and lambda is just cosine alpha, just from the triangle. Okay, so I'm going to write things in the following way. I'm going to write this like this. So I'm going to write cosine alpha k is equal to k delta of so alpha, or if you want, you prefer alpha, it depends on delta, or delta depends on alpha, whatever you prefer. But of course, it is clear what's going on in the case when this is a disk, but for a general body, this is not clear geometrically, but but this is the same thing, because what we are going to do, our k will be a very small perturbation, very small perturbation of the disk. So it's going to become clear what I mean, because I'm going to define this angle alpha like for the disk, like in the usual way, like here, and then we are going to perturb our body. So think please like this. So if this, say this is my disk, this is my disk, and then the body is going to be something like this, some kind of star-shaped body, and then we'll make it maybe even like this. Yes, this is the K. This is the star-shaped body. Observe the trick. This will be very important, that when I write lambda K is equal to K delta, this is convex. We discussed this regardless of if K is convex or not. If K is star-shaped. So this means that if we find a solution in the class of star-shaped bodies, we will automatically find a solution in the class of convex bodies as we want, because this guy is always convex. So, and then K is proportional, K delta, yes, because I can erase 1 over lambda, lambda is positive. And so this is the key observation here, that we are going to work in the class of continuous functions, and positive continuous functions on the circle, they exactly correspond to the, maybe let me write it down, positive continuous functions. This one, they correspond in one-to-one correspondent with the radial functions of star-shaped sets. Star-shaped with respect to the origin, of course. And this will be very, very convenient. So let's define the map. So we'll define the map, the key map for us. It will help us to linearize things. So I'll have f alpha rho, or maybe f alpha rho. This is the radial function, and the angle alpha is fixed, the radial function, f alpha rho. This is going to be a map from real numbers times continuous functions on the unit sphere into continuous functions on the unit sphere. Why put here continuous functions? Just continuous functions. The continuous functions. So let me write C as one, continuous functions on the unit sphere. Okay, very good. So we have this map. How we are going to define it? We are going to define it very easily. So this is just to mimic what we have before. This is going to be cosine alpha is rho minus rho delta. This is our map. And our condition that the cosine alpha rho is rho delta, I recall that this is the same as cosine alpha rho k is rho k delta, yes? And this is our lambda. This is equivalent to saying that f alpha rho is 0. Okay, I just want to write it down in the form of the implicit function theorem. Okay, and now, so we want to linearize it. So we want to linearize it. This is the key step and the most difficult case. It turns out that the linearization in the space of continuous functions, and this linearization happens to be easy to find only in the space of continuous functions. If you work in the class of convex bodies, then you need to assume certain smoothness, and then the formulas become very ugly, and it is not clear how to linearize this equation. So let me write this in the informative way, and then I will for me at first, yes, the information. Yes, so I'm going to write like in calculus, the increment of this of the result of the floating body, the small change in the floating bodies. This is going to be a convolution of the increment with the body itself, where who is going to be k alpha? K alpha is going to be 1 over 2 sine alpha, the characteristic function of the segment 1 minus alpha alpha. I recall that characteristic function of the segment of, let's say, of theta, this is 1 if theta between alpha and 0 otherwise. Okay, so this means that our operation, so we should think that after we linearize, you remember I wrote this cat with mustache, yes? So this is just a convolution in our case. I will formulate in a moment the precise statement, but I'm not sure if the precise statement, I'm not going to have time, unfortunately, to prove it. So how much time do I have left? 10 minutes? Do I have 10 minutes?
Yes, please.
Okay, very good. So what I'm trying to say right now, informatively, is that this convolution operator is very convenient, to tackle using the Fourier coefficients. So this is what is going to help us. Let me write it down again. I will write like I recall that I had this f alpha of rho is equal to 0. Now I'm going to write it as in calculus df alpha of delta rho. This is cosine alpha delta rho minus delta rho delta. And then, there are two deltas, delta little, delta capital. This is sine alpha delta rho minus this convolution with this operator delta rho is equal to 0. This is going to be our equation. Let me formulate the lemma precisely. Just one thing I wanted to formulate. This is the most difficult part of the proof. And unfortunately, I don't have time to prove it, but you will believe me. So for any epsilon positive, there exists some number eta, depending on kappa, depending on epsilon positive, such that if you have two bodies close to the unit disk, this is kind of almost differentiability, quasi-differentiability. So if you have two bodies, rho, let me write rho 1 minus 1 in the space of continuous functions less than kappa, and I have also another body, rho 2, any two close bodies to the unit disk on the plane. And if I have them close, then I have the following inequality. If I have the floating body for the first one, and I have the floating body for the second one, this is what I meant when I wrote the increment. Delta rho delta. Yes, this is like in calculus. Yes, minus 1 over, I will write precisely everything. 1 over 2 sine alpha. The integral is going to be theta minus alpha, theta plus alpha. And here is going to be rho 1 of tau minus rho of 2 of tau, d tau. And the absolute value, and this is less or equal. And now this is going to be constant, omega, and here is going to be rho 1 minus rho 2 in the space of continuous function on the disk. So this is exactly what, this is the precise statement. What I meant, this is my delta rho, like in calculus. So if you have a small increment on the body, if you perturb the body a little bit, then the floating body is going to be perturbed also a little bit, and it's going to be very close to the convolution operator. So again, please think for the rest of the talk that this doesn't exist, is 0. Yes, and then I'm going to write this, that this difference, yes, is approximately equal to this convolution operator. Okay, I'll come back to this error if we have time, but okay, so what is the moral? So let's have the moral. The moral is that, again, I recall that our differential operator, our linear version, is this identity operator. This is the identity. Cosine alpha minus this convolution operator with our function. And then this is very convenient to attack using Fourier coefficients, the Fourier coefficients. So let me write the Fourier coefficients. L is going to be an integer. Okay, this is the Fourier coefficient. I'm not going to explain this. This is a classical thing. So these are both convolution operators. This is a convolution, obviously, and this is a convolution. So the Fourier coefficient brings it to a product. So I'm going to write this as mu alpha over L, and here is going to be this convolution operator, I mean the Fourier coefficient of the function itself. This is the Fourier coefficient of the function itself, and this is the Fourier coefficient of the operator we are talking about. This is going to be a multiplier. And this multiplier is going to show us what's going on. Observe only that, of course, I recall that, of course, if you maybe, let me go to a different, let me write this again. So if I have this df alpha delta rho, the Fourier coefficient, this is just my multiplier like this. And you can compute this multiplier. This is very beautiful, mu alpha of alpha. This is just cosine alpha because the identity is clear, minus sine L alpha divided by L sine alpha. This is the multiplier. And of course, one can define it for any angle. Yes, alpha. Let's think that alpha is from 0 to pi over 2, if you define it properly. Okay, so the observation is the following. So of course, if you just check this, mu alpha of 2 is 0. Of course, I mean, the identity is the solution of our equation. Yes, if you have disks, we talked about it, then we have the solution. But also the second coefficient, I mean, works because look, mu alpha of 2, what is mu alpha of 2? This is cosine alpha minus sine of 2 alpha divided by 2 sine alpha. Yes, and this is what this is, 2 sine alpha cosine alpha. So 2 sine alpha is going to cancel, so this is 0. This is the strong indication that the ellipses are going to come into the play. And the main claim here, and the main observation, the main claim is that there exists an angle alpha. This angle is going to be very close to pi over 2, such that mu alpha not of fifth Fourier coefficient is 0. This is the key observation here. This is the, I mean, after you prove the lemma, after linearize it, you have this key observation. And could you please tell me, I apologize, could you please tell me how much time I have left?
You have 5 minutes.
5 minutes, very good. So we have this condition. And now what we are going to do, we are going to, so this shows the multiplier is 0. This shows that what? The df alpha of this delta rho corresponding to the proper function we are going to choose. Yes, for example, if you have 1 plus s some small number cosine of 5 tau, then if you apply this differential to what? To this s cosine 5 tau, because of the multiplier, just roll, this is 0. And so this means that this guy, if I write this some auxiliary person, yes, also maybe let me write it like auxiliary some L, yes, of tau. This is going to be the solution of the linearized equation. We need the solution of the general equation, and now this is where this implicit function theorem comes into play. And so, but we are going to apply this implicit function theorem, in the Banach space version. Yes, Banach space version. Unfortunately, I don't have time to enter into this. I have only to mention this is the so-called bifurcation theorem. Bifurcation theory, sorry. And let me just mention the names. So Rabinovitz, Crandall, and Kargaev also used it in a different way with some problems related to harmonic analysis. And so these people somehow already made the way, and we just followed them. So how to show that, given that, so we know that this linearized version has a non-trivial solution, this equation has a non-trivial solution, then how to show that our equation has a non-trivial solution. And this is exactly this implicit function theorem. Let me just finish the thought because I don't want to keep you. So My point is that what do we want? We want to solve this. Yes, we want to find this rho such that our equation, this is cosine alpha rho minus rho delta, has this solution on trivial. Yes, what we are going to do, we are going to choose this Banach space. This is very important. Banach space, this is going to be, I'll write C5 of S1. This is going to be the space of even 2 pi over 5 periodic, yes, continuous functions on 0 to pi. Yes, something like this, because our functions are going to have this symmetry of the pentagon, something like this. So if this is 0, this is your theta. And we are going to work in this Banach space. I don't have time to enter the details. Let me just recall what I was writing. So what are we going to do? We know that there is an angle. We know that there is an angle such that this differential is 0. Yes. So if you write the calculus formula, 1 plus s cosine 5 tau is equal to alpha naught of 1 plus, this is just the calculus formula, s cosine 5 tau and plus some error. Okay, so this guy is 0 because the disk of radius 1 is the solution for any alpha. Yes, this is true for any alpha. This is 0 because we didn't show it, but I just claimed that this is 0 because for the multiplier was 0 here. Let me put here not, and because the multiplier was 0. And so we show that we are almost there. You see, we are almost, this is the error. The question is how to kill the error, and this is done using this implicit function theorem. Let me just maybe write one thing. What should I write? I don't have time to. Okay, maybe one thing I will write. One can show, and this is the last thing. One can show. This is a long story short. One can show that if I have f alpha 1 plus s cosine 5 tau plus some solution that we are looking for 5 tau, and this the function depending on theta, then this is going to be some error term times cosine of 5 theta. Okay, and alpha is going to be very close to alpha naught, and alpha naught was chosen. I didn't have time to explain this. Was chosen using the intermediate value theorem, and now one can show that this guy would have depends continuously on alpha and s, and then one can choose alpha 1 close to alpha naught such that this error term is 0. And this is exactly what we wanted, because this is going to be our solution, our rho. So our solution rho is going to be in this form, phi. Yes, something like this. Let me write of tau here, of tau, where those guys are going to be all, the phi of tau. This is going to be in the form, what cosine, let me write some kind of, what do I want to write? Let me write it like this. I want to write it as some Fourier coefficient ck cosine of k5. 8 and 5k, let me write, sorry. One last touch, 5k tau. This is what I mean, k from 0 to infinity. So what I'm trying to say that all of these functions here, I mean, all of these terms here, they're multiples in the frequency of 5. Yes, 10, 15, 20, etc. And so this is our solution. This is the final solution we are going to have. And this will correspond, S is very tiny, this is small. All coefficients are going to be tiny. So our solution rho of our k is going to be very close to the unit disk. And this is the end of the story. I'm sorry, I was very fast and omitted the details, but this is what we have.
Thank you for the talk.